So hello and welcome to this webinar out of our networking basic series. I am Apurva Todkar from the DE-CIX India Academy. And if you are interested in more videos, feel free to visit our YouTube channel or check out our website at www.dekix.in/dekix academy. So in this series, Networking Basics, we explore the foundations of the internet protocols and how communication works on the internet. So 1 year back, we had started off with the networking basics series. Then we moved on to BGP and some advanced topic. But there was one topic pertaining to ICMP and also ping that I wanted to cover. So in the last session, we covered the topic of ICMP, and this is in continuation to the same only. So today's topic is not exactly as basic as you would think. So today's topic is not exactly basic, like I said, but I would encourage you to keep listening. So we'll be talking about ping and why it is considered harmful for network monitoring. So if you feel like you are missing some background, I would recommend watching my earlier webinar videos on IP and ICMP first. In those, I explain the essential concepts you will need to fully understand today's discussion on how ping and its specific role in network monitoring. Uh, let's take a look at a common situation. So if a customer calls and says like, "Hey, we are monitoring some packet loss towards a target," and do you seem to see the same issue in your network? The help desk then answers that how exactly you are monitoring the packet loss, and the customer generally replies that, "Well, we are constantly pinging your peering router, and we see about 3% of packet loss." Then the customer service help desk would be reaction like, "You do what exactly?" So quite a surprise for customer service. Like, why are you exactly constantly pinging to the peering router on our side? So, and then the customer adds that, but even though we monitor the packet loss with the ping, everything seems to be fine. So we don't really know what is exactly happening. So in this webinar, I'll explain why using ping for network monitoring can be misleading and why it's often a bad idea. So let's start about talking about ping now. So ping exists in both IP version 4 and IP version 6. So you have probably used it before. So typically we use ping to check if systems are alive, meaning whether it's up and running and reachable over the internet, or might as well you can do a ping responses on your local LAN segment also to check whether the nodes are reachable or not. So when you send a ping, you're actually sending a special packet. If the system responds, you get a reply back which tells you that the host is actually reachable. But ping isn't just about sending a packet. It also needs to process the response. So that means it has to match the packet that you have sent with the reply that you will receive. So under the hood, uh, these packets are nothing but ICMP messages, like we said. There's an echo request, that's the packet that you send, and there's an echo reply, the packet that you receive back. In ICMP, if you haven't seen my earlier video, it's a protocol that operates alongside the IP protocol. So it uses IP for transport. And but unlike like TCP or UDP, it doesn't have any higher level protocol sitting on top of it. So in other words, you can say that ICMP is essentially the end of the stack. So it stands on its own, and this is true for both IP version 4 and IP version 6 for the ping ICMP. How does an echo request or an echo reply actually look like? So let's take an example of the echo request here first. So I'll take an example of IPv6 header in this case. So first you have the standard IP header, of course, which includes the source and the destination IP address fields. Then comes the ICMP v6 header. So this is an also important fields here, like the type field is also there here. So type field, this is a 1 byte field. For an echo request in IPv6, the type value which would be included is 128 for this case. And the code is set to 0. And the checksum is also calculated over the header area and the data. And the identifier is also an optional field if you want to add something to it. And then there's the sequence number. There's a sequence number. So this increases with each ping that you send, and then you have to match the request with your replies. So finally, you can add some data to the data field. So its main purpose is to just make the packet size larger. So if you leave it empty, the packet stays small. And but if you want to test it with some different packet sizes, you can just add the data field to see how the network behaves with a larger size packet. So here, as you can see that the ICMP type is 129. So that's what indicates that it's an echo reply now. Okay. Earlier we were talking about the echo request. Now we are seeing the packet for the ICMP echo reply. So, and in here also the code field is set to 0, and the checksum is also calculated over the header and the data, just like in the request that we have seen. And the important part here is that the identifier and the sequence number are copied directly from the echo request. So the values would be the same. Okay. The data field is also copied. So if you are sending out a large echo request, you will receive a large echo reply of the same size. Let's see how a ping is actually processed. So let's take an example here. This is example of an IPv4 example that you can see here. So I didn't go into all of the header details earlier because they were very similar to IPv6. So, but now you can see that the fields are actually filled out. So the source and the destination address along with the identifier field is there. Then the sequence number is also there. The echo request is sent to the target system. The target system then generates an echo reply. To do this, the system generally the system swaps the source and the destination address because now the packet has to go back. So it copies the identifier, the sequence number, and the data field from the request, and that way the sender can match the reply with the correct ping it was originally sent. Right. And here's the important point. So replying to a ping is actually not free because the system has to generate the reply packet, filled in the correct details, and it has to send it back. So all of this requires processing, which is handled by the CPU. So sending just one ping packet might look like trivial, but imagine sending thousands or even millions of ping packets. So that starts consuming the noticeable CPU cycles. And this is the one reason that while relying on ping for network monitoring can become problematic. So let's now see how does pinging a router actually works. So here I have a diagram that shows you how a router operates. So normally when a router receives a packet, it processes it on the data plane and it looks up the forwarding table and then sends the packet out through the appropriate interface. This is a normal way that the router processes the packet. All of this happens entirely on the data plane, which is designed for high-speed packet forwarding. And the main CPU usually isn't involved in the process. The work is entirely handled by the line cards or the ASICs, that is your application-specific integrated circuits on the interfaces, allowing the packets to be forwarded very quickly without the intervention of the CPU at all. So what happens actually when a router receives a ping packet? So in this case, you can see that we have an incoming packet first arrives on the data plane, where the router quickly realizes that this packet is meant for me. Okay. So then, since it is destined for the router itself, it can be simply forwarded to it cannot be simply forwarded to the regular transit traffic, but instead the packet is copied into the memory and the CPU takes over to process it. The CPU then generates an ICMP echo reply, filling in all the required details before sending out the packet back. And for just a few packets, there's not an issue. The CPU is powerful enough to handle that easily. But however, if the router receives a very large number of pings, okay, then things start to change. The CPU can only handle a limited number of this control plane packets at a time. So to prevent this overload, most of the routers then implement a rate limit or an ICMP control plane protection feature. So this means that once a limit is reached, any additional pings are simply dropped without being processed at all. So from the sender's perspective, this looks like a packet loss, but in reality, the router is just protecting the CPU from being overwhelmed by the excessive ping requests. So you must have, like we have many audience who are already connected with the ISP background only, and they might be knowing that whenever they are trying to ping some or the other CDNs, like for example, Google, we get this query quite often that whenever they are trying to ping the global DNS of Google, that's 8.8.8.8, they receive intermediate packet loss whenever they are trying to ping. So we have to tell the customer that please don't do those repeated pings because Google themselves have ICMP rate limits on their side of router. So one set of replies are gone through, then they start to discard those packets, and you see those pattern drops or those number of packet loss whenever you try to do ICMP response. But when you try to access the services, services works flawlessly. So this is one of the examples that I wanted to put through, because our customers generally see those issues whenever they are trying to reach some of the other destination. This is applicable for rest of the other CDNs also, or other hosting providers also, who are hosted over the exchange or also over the internet also. So that is a standard practice that is being deployed by these big companies, because they also want to not reduce the performance by just simply processing those ICMP packets every now and then. So a few, like I said, a few pings is never a problem, but when you start talking about millions of pings, that's a different story. So each one needs to be processed, and that can overload the CPU. So remember, the CPU has more important tasks like running the routing protocols, maintaining the control plane, and not just replying to your ping packet. So there's already a considerable amount of load that's actually being processed by the CPU. So to handle this, routers often use a rate limiter or a policy R to control how many requests should actually go to the CPU. And for example, the rate limiter might allow you up to some, for example, 10,000 pings per second. And anything that goes beyond will get discarded automatically. Even if a router doesn't have such a limiter configured, the CPU itself becomes the limit, because CPU itself has a threshold. So once the CPU is overloaded, it will automatically start dropping the ping responses, because it simply cannot process them anymore for you. So from the sender's point of view, this looks like a packet loss, since no reply comes back from the destination partner. But in reality, the router did receive the pings and it just chose not to process them for you. If you want to monitor your network, like uh, I just told you that this is a problem basically, but monitoring is also a crucial thing that you want to do in our network. So how can we achieve that? Okay. So well, there's a great tool that we have that is called a smoke ping. So didn't I just said that ping is bad? But no, actually ping is also a good tool. But what if what I said is that massive ping floods are bad. Okay. So smoke ping, on the other hand, is quite sensible. So by default, it sends about approximately 20 pings every 5 minutes, so which is perfectly fine and safe for the routers also. So it then presents the results in a clear visual graph, making it easy to track the latency and detect any loss over time. So, okay. And remember, if you notice packet loss in these graphs, it doesn't always mean that's a real network problem. It might simply be due to a policy or on the router, or any ICMP packets sent to the CPU subject to the rate limiting, and not just yours. Okay. So this is also a great tool that you can use in your network. So just monitor the ICMP responses, and you can have a clear visual representation of how exactly are the statistics to those destinations that you have put into monitor. Then another useful tool that we use for performance testing basically is iPerf. So unlike ping or normal ping or a smoke ping tool, iPerf is designed to run on servers and not on routers. To be clear, it's not meant to be run on routers. It's clearly running on servers and the end client devices. So if you really want to measure the performance or the link throughput, you can set up a server or at a target location. For instance, uh, like you want to deliver a point-to-point link to an end customer or a leaseline customer, for example. So how do we actually test it? Usually what ISPs do is they do a speed test or download some sort of a file from an website to see what actually is the packet speed that they are getting. But for instance, if it's a point-to-point link, or the customer demands that I want to check the entire throughput of the circuit if it is going or not. So you can install a target system in a server basically in your network, and you can install iPerf there and make it as a server. Okay, and you can tell the client to have a iPerf test, a throughput test to that server, so that he could then see those statistic of what is the link throughput that he's getting. So he can do a complete UDP and TCP throughput testing of the link. So this is also a great tool. Uh, and you can use it by starting the iPerf command on both the server and the client end and compare the measured result. Okay. So this is also pretty much commonly used tool in day-to-day basis. In our network deployment also, we suggest the end user clients to use this. So this was about it. This was a short topic basically in continuation to the ICMP topic, that why ping is generally considered as harmful. So if you like to check out more, you can check out the official IPOF documentation on their webpage. Okay, so this was about for the today's session. I hope that this was informative, and if from the audience they if they have any questions or any queries, they feel free to ask them right away. We are open to your questions. Also, if anybody is willing to uh, have those slides, we are ready to share it with you. You can just drop down your email IDs in the chat box so that our team can send out those white papers and those PowerPoint presentations to you guys. I hope that nobody is having any questions. I think so. So people can drop down their email IDs. They want those PowerPoint slides. Also, do check out our DE-CIX Academy page on the India website, DE-CIX India, so that you can watch those previous webinars that we have already done. Also, we have an upcoming session on the 28th of November 2025.
Thank you for watching.